Okay guys, welcome back. So this is the third video focusing on regression models, diagnostics and tests of assumptions. So in the first two videos here that I just recorded, I fitted a multiple regression model, and then we looked at the assumption of normality of residuals in the first video, and then in the last video before this one looked at the assumption of linearity. So just as a quick recap, I use the MT cars dataset, which is data about 32 models of cars and various information about them, such as their MPG, their weight and stuff. And I basically fit this really basic multiple regression model using stats models where we used weight and displacement to predict miles per gallon. We found we had a significant model and that weight was a significant predictor of miles per gallon, and it was negatively related to miles per gallon. So the larger the weight, the lower the miles per gallon. And then we check normality of residuals and linearity. And in this video, what I'm going to do is focus on multicollinearity. So a key assumption of multiple regression models is that the independent variables are not too highly correlated with each other. So when independent variables in a multiple regression model are highly correlated, then scores on those IVs are not independent, and scores on one can be predicted by and changed with scores on the other in some sort of systematic way. So if two IVs are extremely highly correlated, then they're capturing the same variability in the DV, and one of them can be removed from the model effectively. You don't need it. They're measuring the same thing. So we can test whether multicollinearity is present in our model by looking at the correlation between our IVs through using plots and correlation coefficients. And if our independent variables have a correlation coefficient that is less than or greater than 0.7, so a negative correlation of negative 0.7 or greater, positive correlation of 0.7 or greater, then they're highly correlated and we're likely to have an issue with multicollinearity of our variables. We can also calculate something called the variance inflation factor, or VIF, for our IVs and use this to assess whether multicollinearity may be an issue. So VIF values of greater than 10 suggest we potentially have multicollinearity. VIF values of greater than 100 indicate we definitely have some sort of issue with multicollinearity between variables in our data set. So what I'll do in this video is I'll look at correlations using the Seaborn heat map method, and then I will calculate the VIF and another statistic called the tolerance, which is kind of the inverse of the VIF. Okay. And we use those to diagnose whether we've got a multicollinearity issue with these two independent variables we used in the regression models, which were weight and displacement. So I'm going to use the Seaborn heat map option to visually assess the correlation between our IVs. So note here that I've specified the correlation method .core, and this will give us the actual bivariate correlation coefficient between weight and displacement. So I'm creating a figure, plt.figure, just so I can specify the size of the figure. And then the method I'm using is SNS, which is seaborn.heatmap, the heat map method, and I'm passing in a list from our data frame of the variables that we want to correlate, weight and displacement, .core, and then a couple of other arguments. I won't say too much about those there, but it produces this nice heat map here. And obviously the diagonals are correlations between a variable and itself. We're not interested in those because we've only got two variables. This kind of duplicates across the diagonal as well. So what we're seeing here is we've got a correlation between weight and displacement of 0.89. Okay, so these two variables are highly positive correlated. So R is equal to 0.89 here. So we probably have an issue with multicollinearity. And what I'll do is I'll calculate two statistics to help us assess the extent to which we have a problem with multicollinearity in our data. So those statistics, I mentioned them before, the VIF, the variance inflation factor, and the tolerance. So tolerance values for each independent variable of less than 0.1 indicate issues of collinearity. And the VIF is kind of, as I said, the inverse of the tolerance. and VIF values for each independent variable of 10 or greater indicate we've got some sort of collinearity issue. All right, so to do this, there's a little bit of coding that I'm going to have to do. I'm going to create a new object called imp_df, just input df essentially, and I'm going to create a new data frame from our original data frame and just containing those two objects. So what you're seeing here is this new object I've created is just, I've just extracted weight and displacement from our original data frame. So they're the two variables we're interested in. And then I'm going to use from statsmodels.stats.outliers_influence, not easy to remember, I know, import variance inflation factor. So I'm importing this method that works out variance inflation factor. And so I'm calling it here and giving it this object as input and a second index of I. But notice there's other stuff I've had to do. I've created this list called VIF, which is an empty list, hence the square brackets with nothing in them. And then I've created this for loop for I in range and then imp.shape. So basically for each observation in range, the shape of this particular object, so it'd be like 32 rows as such. We're then going to append a value to this VIF empty list, so VIF.append, and what we're going to append is variance inflation factor that relates to the particular data frame object we've created. So what this will return is, if I run this, that's not going to return any output, but we now have worked out the VIF essentially. And what I'm going to now do is create a kind of pandas data frame object which will give us the VIF score for our two variables essentially. And to do that, I'm passing a dictionary of key values. So one's just a string, so it's just going to print VIF essentially, and the other is our actual VIF value. So it'll give us two, one for weight, one for displacement, and then index equals imp.column. So it's going to give us one. That's essentially the same thing, two columns. And then I've asked it as this .t is to give us a transpose of the matrix. That's what it does essentially. So rather than it being one column of VIF and then two rows with weight displacement, it's just kind of flip that around. And you can see they've both got the same VIF value. We kind of expected that because we're looking at the relationship just between these two variables. But you can see it's 14.93. If we round that to two decimal places. So recall what I said earlier, that VIF values greater than 10 are potentially an issue, greater than 100 definitely an issue. So we potentially have an issue here. The other thing we can look at is the tolerance as well. So to work out the tolerance, I'm just going to take 1 and divide it by this VIF value here. And if we call that, we see we get a value of 0.669. So 0.07 if we round that to two decimal places. So what we're seeing here is we have a VIF of 14.93 for the independent variables in our model. So this is greater than 10, which was the threshold for potential problems. Likewise, the tolerance, if we calculate that manually there, it returns the value of 0.067, and this is less than 0.1, and that was the threshold for the tolerance. It tells if there's an issue. So these results confirm what was highlighted by the heat map and the original correlation of 0.89. So we have here an issue with multicollinearity of our independent variables. So we've kind of violated this assumption of no multicollinearity of IVs. So we'd likely want to address this, and we could probably address this by just dropping one of the independent variables from the model. We found that one of them wasn't a predictor, a significant predictor, once I'm assuming that displacement wasn't a significant predictor once weight had been accounted for, because of the fact that they are so highly correlated. Okay, so that's all I'm going to cover. So that was what we've done in this video, is look at the assumption of multicollinearity and how we can diagnose whether that's an issue. We did that using correlation coefficients, using the Seaborn heat map, which is pretty cool, and also by calculating the variance inflation factor and the tolerance, okay, and comparing them to a threshold. So in the next video, we will go on and look at homoscedasticity, or constant variance, and see if that assumption has been met or violated for this particular data and regression model. I hope that was helpful. Thank you for listening.